Welcome to the UGC e-Pathshala lecture series in computer science. In this series of lectures, we have been looking at database management system. For today's session, I will be detailing you with relational algebra. The learning objectives for today's session include knowing the meaning of the term relational completeness, how to form queries in relational algebra, to learn the various operations in relational algebra, to understand the foundations of relational algebra. As a general introduction, relational algebra and relational calculus are formal languages associated with the relational model. Informally, relational algebra is a high level procedural language and relational calculus is a non-procedural language. However, formally both are equivalent to one another. So, a language that produces a relation that can be derived using relational calculus is relationally complete. To talk specifically about relational algebra operations work on one or more relations to define another relation without changing the original relations. So, both the operands and the results are relations. So, output from one operation can become input to the another operation. It allows expressions to be nested just as in arithmetic, and this property is called a closure property. There are basically 5 relational algebra operators. Those are selection, projection, Cartesian product, union and set difference. So, these 5 operators perform most of the data retrieval operations that are needed, and we also have other operations like join, intersection and division operations which can be expressed over and above these 5 relational algebra operators. So, I repeat the relational algebra operators, those are selection, projection, Cartesian product, union and set difference. Apart from that, we have joins, intersection and division operations. To give you an image perspective of all these relational algebra operations, the first one indicates the selection, where the highlighted ones indicate the selection. So, this is how we select. So, that happens majorly through rows or tuples. Projection happens through attributes or columns, and when I define two different relations like P and Q, which has values like records like A, B for P and 1, 2, 3 for Q, and if I am to do my Cartesian product between P and Q, it becomes A1, A2, A3 and B1, B2 and B3. So, this is your Cartesian product. If I do a union of two different relations, it includes both the values that is included with relation R and relation S. Intersection between relation R and S will highlight only those aspects which are very common between relation R and relation S. The difference indicates S will be completely omitted from the relation R. Further, there are other operators like join and divisions. If you are introducing two relations like T and U with attributes AB for T and BC for U, if I am to perform natural join, the notation of natural join is this, where it will indicate the common operators, common record values for B will be mapped with A and C. And there is another join called semi join, left outer join, and there is an operator of division. We will look after one another. First, we will perform an operation called selection, which is otherwise called restriction. The notation that is used for selection would be sigma. Sigma of a relation R with a predicate. Predicate is to mention on the condition that we may have to perform for doing this selection operation. So this works on a single relation R and defines a relation that contains only those tuples of R that satisfy the specified predicates or a specified condition. For example, for a selection or a restriction, in case if I wanted to list all staff who are getting a salary greater than 10,000, the same may be notated as select from staff where the salary need to be greater than 10,000. It is not greater than or equal to, which the condition natural language says salary greater than 10,000. Select salary greater than 10,000 from staff. Assume this is the list of records that is available for staff. The condition is to check on the salary greater than 10,000. Only 2 records will be highlighted of the 4 records, which will be the resultant. So the salary greater than 10,000, 18 would be greater than 10,000, 24 is also greater than 10,000, whereas 9,000 is less than 10,000. Only these 2 values will be highlighted, like staff number SG14 and staff number SG5. The complete attribute or the complete record pertaining to these 2 will be selected and will be displayed. So that is what is a selection that we have explained. It has highlighted only the row values or the tuples. The second operation is called projection, where we will represent that with the symbol pi for a relation R, which will majorly list us with a column values, column 1, column 2, column 3 up to column n. And this projection works on a single relation R and defines a relation that contains a vertical subset of R, extracting the values of specified attributes and eliminates duplicates. For example, with the same staff relation, produce a list of salaries for all staff showing only staff number, first name, last name and salary details. So in this case, I am to list the salary for all staff who are working for a specific department, but to highlight only attributes, not all the attributes, only attributes like staff number, F name which is first name, L name that is last name and the salary details. So pi is for projection. From staff I am to highlight staff number, F name, L name and salary. So this becomes the predicate for projection. So I have highlighted staff number, F name, L name and salary, which is this. So this gives all the values, not a specific value as in the previous case we have indicated salary greater than 10,000. This has given all the values whose attributes vary. Again referring to the previous table, this has highlighted only attributes of this particular relation. Now we will talk about union, where the symbol for union is this. Between 2 different relations union can happen. Union of 2 relations R and S defines a relation that contain all the tuples of R or S or both R and S. Duplicate tuples may be eliminated. R and S may be union compatible if R and S have I and j tuples respectively. Union is obtained by concatenating them into one relation with a maximum of I plus j tuples. Here I have highlighted an example for union where I want to list all cities where there is either a branch office or there is a property for rent. So I would appropriately convert this query where I wanted the city list all cities where there is either a branch office or a property for rent. So there are two tables like branch and property for rent table, from where I have to highlight only city as an attribute, which should be union. So, project from the branch relation only city, project from the property for rent relation only city, make a union between these two operator, which will make the value for the union. As I have indicated in the beginning, between two relations R and S, if I am to do union, it will take the maximum of I tuples in R and j tuples in S, but it tries to avoid duplicates. The next operator is set difference, which is indicated by a negative symbol minus. It defines a relation consisting of the tuples that are in relation R, but not in S. So, S is completely to be eliminated from R, but in this case also R and S must be union compatible. So, an example of set difference, for the previous case I am slightly changing that previous property, list all cities where there is a branch office but no properties for rent. So, I have to highlight a particular city where there should be a branch office and there should not be any property that is available for rent. So, project from the branch relation city, project from the property relation city, and make a difference operator between these two, that will say Bengaluru is the only city where there has no properties for rent, but that has got a branch office. So, the same when applied in this set difference, it has got relations only from R, and any property that is assumed with S is to be neglected, and they are union compatible. The next relation that we are introducing is intersection, which is commonality between the both, which is indicated with this symbol intersect. It defines a relation consisting of the set of tuples that are in both R and S. R and S must be union compatible again, and it can be expressed with the basic operators which we have previously seen. R intersection S can alternatively be referred as R set difference of R with S. So, here we have an example for intersection. List all cities where there is both a branch office and at least one property for rent. So, they have to be an intersection, like one property at least need to be mentioned as a property for rent. So, here again I mention project branch from a particular city, project property for rent from a particular city, make an intersection between two. So, a city that has got a branch and at least one property for rent, at least it can be more than, but there should be only one, at least one. So, Delhi, Hyderabad and Chennai has got properties for rent, at least one can be in New Delhi alone, but there is more than one property which is for rent and there it has got its branch office in turn. So, that is intersection. So, to highlight with the actual diagrammatic representation, intersection is a commonality between two relations R and S, which is highlighted with blue. In the previous session, what we have looked at is a Cartesian product between two different sets. Now, we repeat it again with the relational algebra operator between two different relations R and S. So, the Cartesian product is expressed as a cross between two relations R and S. This defines a relation that is the concatenation of every tuple of relation R with every tuple of relation S. That is a cross product between P and Q in this particular case, where if I multiply P and Q, it will be forming different rows, say A1, A2, A3, B1, B2, B3. So, 2 multiplied by 3 would create 6 rows, 2 multiplied by 3 would create 6 rows, those 6 rows are like A1, A2, A3, B1, B2, B3. So that would be our Cartesian product. The other operator is join, which is very important when we are marching towards optimization of a query. This join is a derivative of Cartesian product and is equivalent to performing a selection using join predicate as selection formula over Cartesian product of two operand relations. One of the most difficult operations to implement effectively in an RDBMS, and one reason why RDBMS have intrinsic performance problems. So as I have already indicated, when we are marching towards optimization issues relating to query in RDBMS, this join would help us in maximum. There are various join operations that are to be performed, like theta join, equi-join, natural join, outer join and semi-join. First we will look at what theta join means. Theta join happens between two relations and join is generally indicated with this symbol, where the predicate has to be mentioned. So this theta join defines a relation that contains tuples satisfying the predicate f from the Cartesian product of R and S. The predicate is of the form of a relation R dot AI, where AI is an record of that particular relation theta, S BI is a record of that particular relation S, where theta may be one of the comparative operators like less than or equal to, greater than or equal to or not equal to. So this operator, any one of these comparison operators should be there to make theta join operative. This theta join can rewrite by using basic selection and Cartesian product operations of the form R theta join of S is equal to select, the sigma indicates select, R Cartesian product of S with the same predicate. So a degree of theta join is the sum of degrees of operands relations R and S. If the predicate f contains only equality, the term equi-join is introduced. That means if my constraint or if my condition to the theta join as a predicate has got only equal symbol, then this theta join is called equi-join. The second join that we are trying to introduce is natural join, which happens between two relations R and S. An equi-join or a natural join of two relations R and S over all common attributes X. One occurrence of each common attribute is eliminated from the result. So this does not have any duplicates. So this indicates the natural join that is happening between two different relations T and U. T has got two attributes A and B and U has got attribute B and C, where B is seeming to be common between two different relations. In this specific case, if we look at 1, B has two 1s here. So it will be mapped like A1x, A1y, which will be the resultant of this natural join between two relations T and U. The other operator that we introduce within this join is outer join. This outer join is basically for the purpose of displaying rows in the result that do not have matching values in the join column. Use outer join. So outer join is notated with a symbol like this, where for the equi-join we had a line here, this has been eliminated and this becomes a symbol for outer join. So this is called left outer join, is join in which tuples from relation R that do not have matching values in common columns of S are also included in the result relation. So this is your left outer join that happens between two different relations T and U. T has A and B and U has B and C in the previous, as in the previous case, where after performing left outer join I will have A1x, A1y and B2 which cannot be mapped. So, the left part of it will remain the same, that cannot be mapped with the right component of it. So, 3z is completely eliminated and the resultant has a1x, the duplicates basically been avoided, it cannot be a11x, the duplicate is b here. So, it has been represented only once. So, it becomes a1x, a1y, and because it is left outer join, it is called b2 alone and this becomes a null value. And the same if it is supposed to be a right hand side value, so it becomes a right outer join, the symbol will completely change it the reverse way, and thus that will indicate a1x, a1y and a empty or a null value with 3z, which will indicate a right outer join. And the last operator with the join is semi join. This semi join is represented with a notation, a half join with a predicate between two different relations R and S. A semi join defines a relation that contains the tuples of R that participate in the join of R with S, and this can be very well returned in term rewritten with projection and join operations, basic projection and join operations. R semi join of S is equal to projection of R equijoin of or natural join of S with an predicate A, that we have represented here, semi join, where we have considered the same two attributes, the same two relations T and U. Semi join basically gives A1, 1 is being considered here, so it has to represent only those values which are on the left portion of it, but not the last value of the right portion of the relation. So, it gives only A1. The other operator which is very common with the relational algebra is division, where division with the divide symbol between two relations R and S defines a relation over the attribute C that contains a set of tuples from R that matches a combination of every tuple in S, expressed using basic operations like project relation R with a condition T1, project S cross this T1 minus R, that is a set difference with R with a condition, then T1 minus T2 will be your actual T, which will be your complete division. So, as I have indicated on the division, I have two relations R and S. This R has got this setup and S has got this relation, but when we divide R with S, the entire portion of this will go off and the remainder is only the shaded portion here. And looking at the another example of division between two relations V and W, where AB are the attributes of relation V, B is the attribute of relation W. When I try to divide V divided by W or V division W, then it gives only values of A and B and it has not been duplicated, because I have considered B with 1 and 2 values, 1 and 2 values are basically being checked here, 1 and 2 appears with A and 1 and 2 appears with B, but the resultant is to be displayed only once. So, it avoids duplicates. So, the resultant will be a relation A with the values or the records A and B. So, the basic points that we may have to think while working with relational algebra operators. Relational algebra is a high level procedural language. The various relational algebra operations that we have used are selection, projection, Cartesian product, union, intersection, set difference, and further we have introduced join. Within join we have introduced theta join, equijoin or natural join, left outer join, right outer join and semi join. Thank you.